In section 8.5, we're looking at two types of inequalities: polynomial inequalities and rational inequalities. So we will start with the polynomial inequality. First of all, to follow our procedure, you need to make sure that your inequality is in the form f of x less than 0 or f of x greater than 0. And you also could have f of x less than or equal to 0 as well as f of x greater than or equal to 0. And f is a polynomial function. So to find the boundary points, you solve the equation f of x equals 0. We locate these boundary points on a number line and use them to divide the number line into intervals. We choose one representative number within each interval and evaluate f at that number. If the value of f is positive, then the function is greater than 0 for all numbers in the interval. If my test number makes the value of f negative, then the function will be negative or less than 0 for all numbers x in the interval. So the test number represents what all the other numbers do to the function in terms of making the function negative or positive. Then we'll write the solution set, selecting the interval or intervals that satisfy the given inequality. So let's take a look at applying this to this inequality. And notice that this is simplified because it's already in factored form. So one of the challenges will be actually getting your expression in factored form once you have a 0 on the right side of the inequality. So the first step is for me to get a 0 on the right side of the inequality, and that step is actually done. So I don't need to do anything to make that happen. That step is already done. Next, I want to solve the inequality where the function is set equal to 0. So the polynomial function is x plus 1 times x plus 2 times x plus 3, and that polynomial function gets set equal to 0. And I'm going to apply the 0 product property 3 times. So x plus 1 is 0, or x plus 2 is 0, or x plus 3 is 0. If x plus 1 is 0, that means x is negative 1. So I would replace all of the x's with negative 1. And then this inequality would equal to 0. If x plus 2 is 0, x is negative 2. And if x plus 3 is 0, x is negative 3. So we've completed step 2. These numbers are our boundary points, or boundary values. These are the numbers that make the polynomial 0. All right, next, we're going to locate these boundary points on a number line. So there's negative 3. We'll put negative 2 here. Negative 1 here. Now notice I've made these open circles because when we go to this next step, we're only testing to find out what numbers that aren't boundary points will do. And also, because our inequality wanted to know when our polynomial was less than 0, the boundary points will not be included in the solution set because they're the values that make the polynomial equal to 0. Now, even if they are included in the solution set, when we set up our test values, as we're getting ready to do in our next step, we are not testing the boundary points because we already know that they make the polynomial equal to 0. But we're testing all the other numbers in the set of real numbers. So this portion of the number line represents the non-boundary values that are less than -3. Here are the non-boundary values of x that are between -3 and -2. Notice I'm writing the intervals that represent all of the real numbers that are not boundary points. So this next interval are all the boundary points, all the non-boundary points between -2 and -1. And the fourth interval are all of the boundary points that are bigger than -1. So notice you'll always have one more interval than you have boundary points. So if I have 3 boundary points, I'm going to have 4 intervals. And these are called test intervals. If I have 2 boundary points, I'm going to have 3 test intervals. If I only have 1 boundary point, I'm only going to have 2 test intervals. Okay, so what we're going to do is we're going to pick a test number that lies in each interval. And where you have to be careful is that you actually are picking a test number in the interval. So anything smaller than -3 can be used as a test number. I'm going to use x equal to -4. And this -4 is going to represent all the numbers in this interval. Here I want to use x equal -2.5 as my test interval. Here I want to use x equal -1.5 as my test number. And here I want to use x equal to 0 as my test number. All right, so remember our inequality. So all we want to do is put the test number into this inequality. So let's put in x equal -4. We'll have -4 plus 1. That actually is -3. Times -4 plus 2. That's -2. Times -4 plus 3. That's -1. So notice if x is -4, we get -6. We get -3 times -2, which is +6, times -1, which is -6. And so our question is -6, so if x is -4, this whole left side becomes -6. Is that less than 0? And that's true. The inequality is true if x is -4, because the inequality becomes -6 less than 0. And that's a true statement. So that means all of the numbers in this interval make this polynomial less than 0. If -4 made it less than 0, and my intervals are set up correctly, all numbers in the interval will make the polynomial less than 0. So now let's test x equal negative 2.5. Negative 2.5 plus 1 is negative 1.5. Negative 2.5 plus 2 is negative 0.5, or negative 0.5. Negative 2.5 plus 3 is 0.5. So I wind up with positive 0.375, less than 0. And that's actually a false statement. 0.375 is not less than 0. So that tells me all the numbers in this test interval will make this inequality false. All right, now let's test x equal negative 1.5. When I add 1 to that, I get negative 0.5. When I add 2 to negative 1.5, I get 0.5. When I add 3 to negative 1.5, I get 1.5. So my question is that greater than 0? This becomes negative 0.375 less than 0, which is a true statement. That number is less than 0. So my test number, negative 1.5, makes this inequality true. So all the numbers in this interval that this test number represents make the inequality true. Now let's test x equal to 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. And we want to know, is that less than 0? Well, obviously this is 6, so the inequality becomes 6 less than 0, which is false. 6 is not less than 0. So that test number makes the inequality false, so all the numbers in the interval make the inequality false. So my solution set to this inequality consists of the union of the two intervals that make the inequality true. The first and the third intervals. So the solution set are all the numbers smaller than negative 3, united with all the numbers between negative 2 and negative 1. And you could actually test some numbers in these intervals to make sure that they really make the inequality true.